In this video, I want to talk about three major examples that are going to come up again and again throughout our discussion of group actions and applications of group actions. So the first one we've already seen. G acts on itself by left multiplication. So remember, acts on itself means that we're taking our set X to be equal to the group G. So we want this map from G cross G to G. We just have to say, how does an element G act on an element X? It just sends it to the product, G times X. So we've already seen in detail why this is a group action. So our second big example, G acts on itself by conjugation. So again, we want to map from G cross G to G. How does G act on X? It sends it to GX G inverse. So why is this a group action? Well, it needs to satisfy two things. One, how does the identity act on X? Well, it sends the element X to 1X 1 inverse, but that's just X. So that's easy to see. And then how does G1 act on G2 acting on X? Well, it's G1 acting on G2X G inverse, which is G1 G2X G inverse G1 inverse. But that is G1 G2 X G1 G2 inverse, right? When you take the inverse of a product, you have the inverse of each of the elements, but the order switches. So this is G1 G2 acting on X. And this is true for any X, G1 and G2. So this conjugation action satisfies the things necessary for it to be a left group action. So our last big example is take any subset H of G. So when I write G mod H, this is not necessarily a group because I'm not assuming that H is a normal subgroup. But it is a set. So it's a set of left cosets of H and G. G acts on this left coset space by left multiplication. So how does a group element little g act on a left coset of H and G, which looks like A times H? Well, it just sends it to the left coset of H containing G times A. So that's the set of everything that's this chosen element G times something in the left coset of H containing A. So why is this a group action? Well, how does 1, the identity, act on AH? It just sends it to AH. So every element is fixed when you act by the identity. So what do you get when you take G1 and you act on G2 acting on this coset? Well, it's G1 acting on the left coset of H containing G2 times A. And that is the left coset of H containing G1 times G2 times A. And that's the same thing you would get if you took the group element G1 times G2 and you acted on the coset AH. So again, it's easy to check that the action that we've defined this way satisfies the things necessary to actually be a left group action. So I'll say a little more about this, but first I just want to note that example 1, left multiplication, G acting on itself by left multiplication, is the same thing as example 3 in the situation where H is the trivial subgroup. Because in that case, what does a coset look like? The left coset of the trivial subgroup containing A is just the single element A. Okay, so I'll pause and erase. I'll say a little more about these three examples, and I'll also introduce some new definitions and see how and if they apply to these examples. The three major examples of group actions that we just defined give rise to additional group actions where you change the set X a little bit. So when A is a subset of G, if you take the set of everything that can be written as some little g times something in A, you get a set that has the same size as the size of A. So you can take this action of G on itself by left multiplication and see that G actually also acts on subsets of G of fixed size by left multiplication. That for each fixed little g, you're getting a permutation of the subsets of fixed size. Okay, something to note is if H is a subgroup of G, the set of things that you can write as little g times something in H, that is the left coset of H containing little g, is not usually a subgroup of G. I mean, it'll be a subgroup if it is the set H, but otherwise it won't contain the identity. All right, so another example like this. When you have a subset A of G, the set of things that are in GA G inverse, so that can be written as little g times something in A times G inverse, this has the same number of elements as A. So G acts on subsets of G of fixed size by conjugation. So you take a subset of given size, you conjugate, you're getting another subset of that same size. So for each little g, you're getting a permutation of the subsets of G that have fixed size. But now something interesting happens. If you have a subgroup H of G, GHG inverse is also a subgroup of G. So G is acting on the set of subgroups of given order by conjugation. And this action is going to be really, really useful for us going forward. So I want to define one more term, and then I'll see how this term applies to the group actions that we've talked about. A group action of G on X is called faithful if different elements of G act on X in different ways. So what does that mean more formally? If you have two different elements of G, let's say G1 and G2, your action is faithful if there's some element in your set, some little x, such that G1 acting on X is not equal to G2 acting on X. That there's some element in your set that distinguishes how G1 is acting from how G2 is acting. So if you have the identity acting on X, it sends every element to itself. So if you have G1x equal to G2x for all x, then using the property of group actions, you can then take G1x and G2x, which will be the same, and you can act on the left by G2 inverse. So you'll see that G2 inverse times G1 is acting by the identity on your set X. So this is how to see that an action is faithful if and only if the kernel of that action is trivial. So I've just sort of described the kernel in terms of the elements of your group that are acting the same way that the identity acts. And remember, you can also think of this kernel as the kernel of the homomorphism that you get from your group action that goes from G to the symmetric group on X. Now that we know the definition of what it means for a group action to be faithful, let's look at the three big examples that we were talking about earlier. So action one, that is G acts on itself by left multiplication, this is always a faithful group action. So different elements always act in different ways. Action two, that is the action of G on itself by conjugation, is faithful if and only if the center of G is trivial. So why is that? What does it mean for G1.x to be equal to G2.x for all x in G? Well, that just means G1x G1 inverse equals G2x G2 inverse for all x in G. And just moving things over, moving G2 over to the left side and G1 inverse over to the right side, we see that this is equivalent to saying G2 inverse G1x equals x G2 inverse G1 for all x in G. So what does that mean? That exactly means that G2 inverse G1 is in the center of G. That's the definition of what it means to be in the center. So these two elements act in the same way if and only if G2 inverse G1 lies in the center. Okay, action three. G acts on the coset space G mod H by left multiplication. So what does it mean for two elements G1 and G2 to act the same way for every x in our coset space? Well, what do those cosets look like? They're some elements of the group little g times h. So G1 and G2 act in the same way on the left coset of H containing G, if and only if the left coset of H containing G1G and the left coset of H containing G2G are the same for all G in the group. So if this first line holds, then it continues to hold if you change the representative of the coset from little g to some other element in that same coset. Nothing changes. And the left cosets of h and g partition g. So if this statement holds for every left coset, then the second statement holds for every g in the group. So, okay, what does it mean for the left coset of h containing g1 times g to be the left coset of h containing g2 times g for all g in the group? Well, we have a condition for when two left cosets are equal. You can phrase this as saying g inverse, g2 inverse, g1, g is always in h for every g in g. Okay, so what does that mean? Well, moving getting rid of this second g by multiplying on the right by g inverse, and this first g inverse by multiplying on the left by g, this is equivalent to saying that g2 inverse g1 lies in the intersection of all of these sets of the form g, h, g inverse. And remember, these aren't just sets. Conjugation sends subgroups to subgroups. So this is equivalent to saying that g2 inverse g1 lies in the intersection of all of these subgroups. So what does it mean for this action to be faithful? That's saying that as you vary over all g in the group, the different subgroups g, h, g inverse have trivial intersection. That's enough to imply that the only g2 inverse g1 that occurs in here, the only g1 and g2 that act the same way, would be when g2 inverse g1 is the identity, which means g1 equals g2. So just to zoom in on this subgroup, it is a subgroup because it's the intersection of a bunch of subgroups. In fact, it's a normal subgroup because it is the kernel of this conjugation action. So it's a normal subgroup, and you can show as a little exercise that it's the largest normal subgroup contained in H.